Oh yeah, now it's visible.
Just a moment. Okay, got it. Just a moment.
Yes, sir. Please take your time.
Yeah. Now I think everything is visible.
Oh yeah, it is visible. Please go ahead.
Great. Finally. Okay. So, good evening, everyone. Once again, it's my fault. So I keep you waiting for at least 5 to 10 minutes. So anyway, so let's get started with the topic. So, as host has already announced this, I am Dr. MRUTYUNJAY Maharana. I work as a assistant professor in School of Electrical Engineering, Jiangsu University, China. This project we had carried out last year, and recently it is ended in December. And it's collaboration with Biotrafo. European Union has sponsored this project, along with the QTech, Q Switch Technology, and Jiangsu University. All these three has collaborated this project. And basically, the objective of this project was the investigation of the partial discharge inception voltage of the biodegradable ester oil with varying temperature. It's a very interesting phenomenon. As everyone knows that moisture is a very dangerous parameter for any insulating liquid when we are using it in transformer or any other insulation device. The moisture create a lot of problems, and it is really notorious to measure, and its parameter are really, how may I say, really dangerous sometimes for the insulation device. So what we thought, like we need to figure it out. We need to quantify how much moisture is creating, what is the problem inside the insulation. So, and also with the temperature, how this moisture is really behaving. On that perspective, we have worked on this project. So in this seminar, we will be having the introduction, experimental method, result obtained, summary, and some future scope or work we can discuss. Since the entire group of mine were working in the transformer, so mostly I'll be talking with the transformer and transformer oil along with its insulation parameter and insulation degradation, how we can monitor it, and what is the necessary prevention we can take it. So as we know that transformer winding are consist of two major insulating objects. One is oil, another one is paper. So there is a very interesting relationship between oil and paper. Paper is always hungry for water, and water inside the oil you cannot control. So when someone is really hungry for the water, if some amount of water inside the oil will be there, then definitely goes into the paper. So, and due to oil, what could be the necessary problem that could cause in the transformer and its entire network, that we can see in the next slide. When it, and in these slides, it tells about the major factors from where this moisture is being coming, like some are the residual moistures, and due to the breathing during the load cycles, poor ceilings, installation, the timing of installation if you will not take the proper care. And there is always a, because moisture, as I told you, it is always a residual parameter. Sometimes due to the paper degradation, because paper consists of cellulosic link. So sometimes the residual water is also developed inside the transformer. So I'll take you the just quantitative data about the water and insulation, how the insulation being categorized, what are the percentage of insulation, and how the water is being distributed. This data is from IEEE PEC seminar Vancouver 2008. So the entire insulation weight distribution in the transformer, oil carries the 90% of the weight that we are all agree about. Then in the left part, you can see the thick and thin. Thick, I consider it for press board, And thin, we can consider about the craft paper, those who know about the transformer. And the winding is being covered with the craft paper. And there is some insulation barrier is being created using the press board, and it is a bit thicker. And the water distribution, if you see, thick part taking the 55% weight, thin part taking the 22%, and winding also carries 22% weight. And the oil is having only 1% of weight. This is why it is so different, because we can consider that oil carries the most of the water. But in the real scenario, all water is being absorbed by the solid insulation, for example, craft paper and press board. We have not studied about the winding because the most of the water, around 77% of the moisture is being absorbed by the cellulosic link. So that is the major motivation. And again, another thing I would like to address here, like the moisture in the paper is very difficult to measure and nearly impossible to measure the exact amount of moisture that is being carried out in the paper. That is why we generally measure the moisture in the oil. So here, moisture in the insulation can lead to the water condensation. Moisture in the winding in paper is critical because it reduces the dielectric strength, as we all know. Increase the risk of buckling at high load, accelerate the rate of insulation aging. Aging is also, again, a very important phenomenon. People around the globe is working on the different kinds of aging. Some is working on the oxidative aging, someone working the accelerated thermal aging. And due to aging also, there is a degradation in the insulation occurs. Moisture in the press board barrier is a critical, reduce the dielectric strength both in the winding as well in the oil. Oil moisture in oil can be measured. Only the, as I told the previous slide, that oil in the moisture in the oil only can be measured. So that is the measure thing that we take it forward, so that we can check if this moisture present in the oil, what will be the issues further. So broadly, if I'll tell you that transformer is a agent who maintain the insulation, stable insulation, as well as the cooling. Transformer oil, the major characteristics is like cooling and insulation. When it combined with the paper is having multiple parameters, like it has the mechanical strength, it has the chemical structures, and both when it combined, it's very difficult to maintain its strength and rigidity for a long period of time. Most of the time, due to the weakening of the solid insulation such as craft paper and press board, generally transformer is being deployed to maintenance, and they remove the papers and press board and make it a new one. New press board and new paper has been supplied. So generally, when it's combined with the heat, generally there leads to generate the peroxide, acid, waters, and these three combinations are deadly, and they produce slots which contain maybe some ferrous particles. There may be some carbonized content. When this particle will be circulated in the oil, in the functional transformer, that will leads to create some hot spot. There may be create some uneven temperature distribution, and there may be temperature gradient. So this will lead to the uneven response of the transformer, which is not at all expected in the case of when you consider the stable transformer of more than 95% efficiency. So there may be incapable to handle the power frequency, failure in the transformer, hotspot formation. These are the issues we are going to face when they will combine and there is a formation of sludge. So as we got the motivation of how that the moisture is the villain here, so we need to carry out how much problem it will create when there will be a moisture in the transformer oil, and what is the maximum limit. So effect of moisture and temperature in the dielectric properties of the oil, because we took the two parameters, or you can consider these two variables here. One is moisture and another one is temperature. Both are dangerous thing for a transformer. So since we know that why we are using the partial discharge analysis, because we need to understand that before a breakdown, what are the characteristics or what are the driving force which are acting in the oil. That is why we need to figure it out the pre-breakdown phenomena. That's why we need to understand the partial discharge behavior of the oil at different temperature and different moisture level. To be very basic and a layman language, we need to understand what happens before the breakdown. If there is a partial discharge because of the temperature, because we consider that sometime it got to high because of the over voltage, and there is a huge temperature distribution, and sometimes the also the transformer blast, why it is happening. So before the breakdown, we need to understand whether it is temperature or whether it is a moisture. So we generally followed the IEC 60270, and we carry out the different experiment. In the later slide, I'll just explain the different procedure we followed for the starting from the experiment and all. So as we used in this experiment, this particular project, we have used 2 oils, and later we used third oil that I'll show you here. But first 2 oil are like FR3 is from Cargill, and PFAV, palm fatty acid, which is from Lion Corporation, Japan. They have supplied this to different oil, and because we consider it's a ester oil is the next as new as oil, because most of the transformer companies and the global leaders are suggesting that we should go for the carbon neutrality and go for the biodegradability of the oil. That is why mineral oil is taken as the reference, but not in the active analysis of here. We have considered both the oil, because it is biodegradable in nature and it's environment friendly. That is why we took palm fatty acid. Again, it is from like ester oil sources. And again, another one is your FR3. It is soybean oil, and it is being largely used for green transformer oil. So here, before carrying out the experiment, we need to just take into consideration like what is the moisture in the oil. So for that, we need to dry the oil and degas the oil. There is a vacuum pump. This is a very basic mechanism. We just suck the oil from the container, from the sample oil, and put it in a degassing chamber, and then put into a, again, that V1 and V2 are the 2 valve. One way will vacuum the container, another valve will just put the oil, degassed oil. These are the basic mechanism we put in the. That's why we confirm that this is the gas free and moisture. We cannot say moisture free, just we can see that the moisture is being very much lower, and we can calculate that moisture. We can remove the added moisture which was previously comes with the company. So again, if I that previous slide was for moisture, this slide was for is for your temperature. Here, if you see the second step, if you see here, second step is for your heating. We cannot heat the oil in the open atmosphere. That is for sure. So what we did it in a nitrogen environment. So we need to see because nitrogen is an inert environment. So we put nitrogen cylinder and with heating, and we put the moisture inside the oil, because this the container, iron container, which is on the magnetic stirrer, that have water, and that water boils at 100 degrees centigrade, and that steam will be poured into the oil. And since that we have to operate that water in a very nitrogen environment, so nitrogen gas is being poured into the first one, and second chamber, this moisture will be poured into the the green color FR3 container, and the temperature is being closely regulated with the temperature sensor over here. I think everybody could see that picture. So again, after getting that desired temperature and desired moisture level, we go for the measurement of moisture, and we use the very traditional method called pressure titration method. Those are working in the liquid dilator must use mostly using this moisture measurement technique. So we measure the moisture. This is experimental methods. So this is the only basic experiment we carried out. That heat and moisture, put the heat and moisture. We need to go for the absolute moisture content in the result section. What we observed, like with the temperature, so we went for like 30 degrees from room temperature to 80 degrees centigrade. Both the oil we consider, and every oil we choose a 10 degree step, and 30, 40, 50, 60, 70, 80. So we took 6 measurements, and in the each case the pattern was same for PFA and FR3, both the cases, absolute moisture content. Why I'm repeating this sentence like absolute moisture content, we can understand in the further slides. Like absolute moisture means the moisture which is exactly present in the oil. So in the table, if you see the first oil sample, temperature ppm, fresh, and after degassing. So initially I have mentioned like fresh condition when you bought from the company, it was 108. After degassing, it is 78. So, and when we raise the temperature of 40 degree, it went to 157, 50 degree, 168, 60 degree, 184, and so on. Same for PFA also. Initial moisture was 42 ppm parts per million, and later on temperature moisture was 22 after the degassing. And later, when we increase the temperature, and the moisture keep on increasing. There is no such comprehension we can get from this. Just we need to evaluate like what is the response of moisture to the temperature, that we can consider in the later stage also. So our main objective in this particular research was to find out the relative saturation moisture content. And why it is very important, if someone will be carrying out the research on the oil, he must have heard about the Cargill report in 2000, Sigre report in 2010. They have mentioned this graph. I think I'll zoom in a little bit to get. So they consider like moisture saturation should be for the different oil. For mineral oil, the blue color. Suppose the moisture saturation at different temperatures. Suppose 80 degree moisture saturation should be around 110, like 200 degrees, 200 ppm. But for the natural ester, such as our PFA and FR3, at different temperature, they have mentioned like different saturation level. We need to figure it out from the actual moisture. What is the saturation level? And this is the formula we have used, that relative moisture content equal to water present in absolute condition divided by saturation condition. Saturation condition we can find out from this graph. We took this graph as a reference from the Sigre report, and absolute moisture we have calculated, and we have considered different relative saturation moisture content of the oil. So from this graph, right of the slide, you can get the relative moisture content for FR3 and PFA. As the temperature increases, I can say that there is a increment in the relative saturation moisture content also, since the actual value is increasing, there is also a relative saturation moisture content is also increasing. But beyond 70 degree, I found that there will be a stabilization of moisture content. Maybe if you will go for 100 or 200 degree, that we have not considered because high temperature operation was not possible at that point of time. So we have limited to 80 degrees centigrade. Later on, I'll analyze this thing in the next slide also. So in the experimental method also, we have studied in the relative saturation moisture content, we need to analyze the breakdown voltage. In the left part, the exact setup, and we have used the spherical electrode. Due to the lack of transformer rating, lower transformer rating, we can go up to maximum of 50 kilovolt. So people may ask question why you choose 1 mm gap. That's the reason, because if you decrease the gap, so in the less applied voltage, you will get the breakdown. That is why I use the spherical electrode, 200 ml cuff and 25 mm spherical diameter, and we gap distance was 1 mm. Generally, people across the globe follows the standard of ASTM 1816, but it can go up to like 50, 60, 70 or 100, but there is a rating problem in the transformer, so we went up to maximum of 50 kV is available, so we went to 1 mm gap distance was decreased, and we measured the different like AC breakdown voltage of the wire. So what interesting thing we observe here, as you can see in the left part of the graph, so we are measuring the AC breakdown voltage. With the increase in temperature till 50 degree, the moisture, the breakdown voltage, we can say like it is not very much fluctuating. Like if you can see the standard deviation also, the moisture with the increase in relative saturation moisture content, the breakdown voltage is not that much fluctuation range, not very high fluctuation range. But beyond 60 degree, beyond like 50 degree, I can say, beyond 50 degree, it is in a high spike, you can get a significant difference in their dielectric strength. The reason for that we have analyzed in the further slides, but we need to note this that before 50 degree and after 50 degree is the standard mark for us. Like we need to evaluate why it is happening like this. There is a reference we have taken like temperature dependence of the breakdown voltage from one of the scientists, ROJS from Japan. He has published this in IEEE DIS. He also experienced the same thing, like beyond 50 degree, they also observe a increment in the dielectric breakdown, but they have tested in different way, like they have observed this breakdown voltage of impulse. Just we have taken their reference here. But the reason for that we have analyzed in the analysis section. Maybe that will be helpful for the further analysis of high temperature. So here we need to understand the reason for alteration of AC breakdown voltage. So as we analyze the thing, so we found there may be, I can say there may be two possibility. One is like charge density. Second one may be the volume resistivity. So in this first graph, charge density of the oil, in the both the cases, in our cases, it is decreasing. Density of the charges decreasing with temperature. That means the charges are not getting accumulated with each other. That is the first reason we have cited this. And volume resistivity is also another significant possible physics behind with the high temperature and decrement of dielectric strength. So volume resistivity is the resistance to the leakage current to the body of the insulating material. And we can say that like the higher the surface volume resistivity, the lower the leakage current and the less conductive the material is. Again, the less conductive indicates that if the material is less conducting, that means the breakdown voltage will be higher. So again, we follow the same article where it has mentioned this mechanism. So we consider this like we're in the correct path. So still we need to figure it out why it is happening. So again, initially we got the breakdown voltage. So we need to find out the reason for breakdown. So we need to understand that what is the partial discharge insertion voltage of that particular wire. So we use the needle plane electrode. You can see the circuit diagram of the entire arrangement for partial discharge arrangement. I would like to explain this this graph here. This is the real-time image of the needle plane electrode, and the needle is of 5 micrometers needle tip radius, and we use FR3 and PFA, and the gap distance we put is for 5 mm gap distance, and the glass we have put for insulation purpose is of 1.1 mm. This is being calibrated before measuring the partial discharge. We need to understand like whether there is a noise or whether there is a partial discharge. So without the oil, without the needles, we measure the partial discharge of the oil for the calibration purpose, and after that we go for the real-time measurement. And we measure it in a 60 hertz frequency because the rated frequency in Japan is 60 hertz. So these are the experimental setup. As you know that heating of the oil, we need to understand like in a very close environment, we need to understand that what is the temperature, thermal probe, and also use the IR camera, what is the temperature in the surface. Then we go for the, we will put a thermal coating so that the temperature dissipation to the environment should not be in a high rate. Though there may be possibility of 2 to 3 degree tolerance of temperature, but again we try to control this temperature in the container, and we measure the partial discharge inception voltage. So as I know that the PD threshold was 10 picocoulomb, we use 10 picocoulomb, and applied voltage was 1 kilovolt RMS per second, and we measured in two ways. One is a linear approach, another one is a step approach. Step approach I have not mentioned in this particular presentation, but we have carried out that we'll talk maybe sometime later. But here we applied this like 1 kilovolt RMS per second, and we increase up to 15 kilovolt, and again we decrease again to same using the same decrement process. We come down to 30, like because in the initial we have mentioned like we have a transformer whose rating is not very high, so we use the maximum up to 30 kilovolt. So here again this similar kind of result we have expected, similar to the here AC breakdown voltage. Till 50 degree the breakdown the partial discharge inception voltage, and beyond 50 degree the partial discharge inception voltage with respect to the relative saturation moisture content was addressed. So as you see from the table, if you see from the table, when we are increasing the temperature, so let me tell you tell everyone everything, like the moisture content, relative saturation moisture content was up to 15%. Here we have considered up to 15%, not beyond 50%. 15%, 15%. So you can see the relative saturation moisture content ppm is limited to 15% for both the cases. Beyond 15% we have not done. We have done in the later slides. I'll show you that. So here also there is a reverse phenomenon we have observed. Like if you relative saturation moisture content and with respect to partial discharge inception voltage we have studied, and we observed that if the relative saturation moisture content is increasing up to 50 degree, the partial discharge value is decreasing, and beyond 50 degree it is almost stable, and it is some deviation is there around 80 degree. Because of this difference in the behavior, we have studied what is the mechanism behind it. So we need to analyze the chemical formulation and what are the chemical things involved in here. So we need to study this. So for that, here as I told you, like we have studied there up to 15%. Here we have studied up to 50% of relative saturation moisture content. So for each cases we have considered, and we also studied the PDIV and PDEV. If needed, we can study further. Here also the PFE and FR3 relative saturation moisture content of 10, 30, 40, and 50. PDIV and EV both are studied, and there is always a benchmark. You can say 50 degree. Till 50 degree the behavior is different, and beyond 50 degree the behavior is upward. Like PDIV value is increasing. That means the oil is not dependent or influenced by the moisture. That means the oil is not very much conducting. Oil has not like conducting, and it is not allowing the breakdown. There is a possibility. So we have studied those kind of phenomena here. So there will be some molecular disarrangement. So we need to figure it out what to do the possible phenomena involved in here, so that we can conclude that why there is a change beyond 50 degree and below 50 degree and above 50 degree. So here we consider two things for AC breakdown voltage or partial discharge inception voltage, both for the same we have suggested. Like till 50 degree, there is a moisture who is playing the games, like who is taking the lead in decreasing the AC breakdown voltage and affecting the AC breakdown voltage or insulation. But beyond 50 degree, it is the viscosity. As we all know, like with the increase in temperature, the viscosity decreases. Like the more the viscosity, the more the particle will be contaminated with each other, and there will be a conducting path will be easy. Beyond 50 degree, what we observe, like the moisture is not taking the role. Moisture is not playing the role. It is the viscosity who is creating a intermolecular distance between the oil, and there is energy from the heat who is making this oil particle very dynamic, and then not combined with each other for this breakdown. So in all the cases, but here, as I told you, Lion for the PFA and Cargill oil, like PFA and FR3, both are similar phenomena. But in case of Midel, we have also analyzed the synthetic that we'll discuss later. There is some different aspect also, because since we are focusing on the ester part, so we are only focusing on the ester part. Both the patterns are same. So we need to understand the mechanism about the process, why it is temperature over viscosity. As I told it, that if temperature increases, viscosity of the oil decreases and molecular randomness also increases. So here, related to the discharge, if there is a comparison between PFA and FR3, why it is behaving differently. So in case of PFA and FR3, PFA is little bit high viscous compared to the FR3. I did a wrong statement. PFA is a high viscous compared to the, PFA is low viscous compared to the FR3. That is why in the left part, FR3 is there, right part, PFA is there. When there will be a initiation stage of your partial discharge, the kinematic viscosity of FR3 is extremely high compared to your PFA. Therefore, in the low viscosity oil in the shown picture, the decomposed gas generated by the discharge of the oil diffuses and disappear immediately due to low viscosity of the oil. So when there will be initiation of the bubbles, it immediately diffuses in case of low viscosity oil such as PFA. But if there will be a high viscous in your FR3, that bubbles will not go away very easily. In the high viscosity such as FR3, the decomposition gas generated by the discharge in the oil does not diffuses, and that will be combined with each other, and the voltage sharing changes, like there may be an alteration in the voltage. This thought to have caused frequent negative polarity discharge in the gas decomposition of the gas decomposition is possible, and there is a like alteration in partial discharge inception voltage. That's why in this case there will be, you can find the difference in AC breakdown voltage for PFA and FR3. Not very high, but you can find some significant difference. So again, for the effect of moisture, we have found out that there will be two kind of moisture. One will be a combined water, and one will be a free water that will be linked with the oil molecules. Like in case of, forget about the synthetic ester. If you talk about the monoesters and the natural ester, The combined water, which is combined with the molecule in the insulating oil, in case of ester oil, combined water is much higher than of mineral oil because of having oxygen compound in their molecules. As we know that mineral oil does not have the capacity to carry the high moisture or high water content in the oil, but FR3 or ester oil have the capacity to tolerate or include much more higher moisture compared to your mineral oil. So that we measure, that is the free water we measure. If the free water increases over saturation level, water become bubbles. Sometimes if you will see, I forgot to put that image. I also experienced that kind of thing while putting the moisture in the oil. We also experience that there will be little bubbles that will not diffuse, that will not go away, that will be inside, and that is the free water content. So water linkage in the insulating oil, if you talk about the combined water, the amount of combined water depend on the molecular structure of the insulating oil. As I told you, like it has synthetic ester oil has 4 ester group. It has, like here, if you can see, if you see, it has 4 groups in the first figure. It has, it can consider or accommodate more water inside it. And ester group oxygen combined with hydrogen bond, otherwise natural ester like FR3, 3 ester group, or that's why we tell it's like triesters. Monoester groups such as PFA has 1 ester group. Here you can see the figure 3 is monoester and figure 2 is your natural ester. So naturally, those having the high ester group, they will accommodate more water. That's why in the picture I have like synthetic ester will be higher than dry ester, than monoester, than mineral oil. Combined water of tetraester estimate to be high water content, that we already know. So there is free water. Free water is combined with hydrogen bonding each other and making cluster like figure 4. Here in this cluster become large when water can be seen. That, like as I told, the free water is like bubble kind of structure. The binding energy of the hydrogen bond is seem to be around 0.1, that compared to the chemical bond. So it is easily that can form like bubbles or something related to the very free water that you can see. So after measuring the partial discharge, this is the one of the major thing we measured, like whether our equipment is proper or not, whether we have measured the partial discharge or something noise. So we use the VHX 2000 digital microscope to measure the tip radius. So here, if I'll show you, initially you see that there will be a tolerance of maybe 0.1 something, but we measure like diameter was 0.5 microns. And after certain experiment, like initially we go for 3 or 5 shots of partial discharge inception voltage, then we experience that the electrodimension of partial discharge has changed, like it is gone up to 6.2 micron, which is not at all advisable, because the partial discharge maybe because of this roughness of this surfaces on the needle tip. That is why we every time we measure the partial discharge, we change the electrode and we used a new electrode and we measure it like, and we got that result of repeatability. So in the summary, moisture has a negative impact on the insulating oil irrespective of nature and type of the oil. Definitely the fact, whether it's a mineral oil, ester oil, or it's a synthetic ester, moisture in the oil is very dangerous. With the application of temperature, moisture is absorbed from the atmosphere, and the diesel moisture has also been associated with it. Already we had moisture and we put some moisture and we measure it. Above 50 degrees centigrade, SCBTV and PDIV are marginally affected by the moisture content. Partial discharge inception voltage at ramp-up condition FR3 has the highest PDIV at room temperature and it has an elevated temperature. Viscosity plays an important role in oil BDV and partial discharge inception voltage. In high viscosity oils such as FR3, the decomposition gas generated by the discharge in the oil does not diffuse and stagnate there. And the voltage sharing changes that affect the PDIV and BDV at high value compared to the BAV. Combined water of tetraester estimate to have a high water content than triester and monoester. These are the summary we have carried out in this research. So we have published 2 articles, one in the CMD, and I have presented in IWJ Symposium last year, 2022, Sendai, Japan, carrying out this research. So these are the research group. Right to me is Dr. Olmo from Spain, and left to me is Professor Hikita, Dr. Kazako, and one senior researcher from QN Transformer Corporation. So this is that was our last visit to the transformer industry. So I'd like to acknowledge IEEE's SBC IIT Kanpur, Professor Nandan Gupta, and the student community for inviting me for the webinar. Special thanks to Ms. Pratyasa and Munmun for assisting me in the whole process. I also like to thank Biotrafo, Lion, Professor Kazako, Hikita, Mototuche, and Ukai for constantly helping me or supporting me during our research activities. Thank you so much, and we can open for discussion. I think I took a lot time. I think, yeah.
No, sir, it was very engaging. Thank you very much for sharing your experience. So I think all the audience will be eager to ask you questions.
Yeah,
And
please.
you know, yeah, please, audience, please ask questions to Dr. Maharana.
Hello, can you hear me?
Yeah, absolutely, loud and clear.
Good evening, MRUTYUNJAY sir. I'm
Good
Rohit
evening.
from IIT Guwahati.
Yes, Rohit.
Sir, I have seen step 2, the way how you have inserted water vapor into FR3, if I'm right.
Yes.
From
Water
using
step
nitrogen
2.
gas.
Don't worry, don't. I'll just go to the slide. Yes. I understand. Yeah, this one you're talking about?
Yes, sir. Yes, sir.
Mhm.
Have you used in the heating cell? Is there water which is being heated there?
Yes. Heating cell contain water.
Okay. For how much time at a particular temperature have you passed the water vapor through oil?
No, initially we wait for like water to evaporate. So what we did is like we cannot cover the container with water. We cannot fill that container with water. So that
Yes.
gap inside the container should be filled with inert gas, not the moisture. Okay.
Okay.
So that is why we put, let's say that container consists of 1 liter, 1 liter that can accommodate the water, but we put 500 ml and rest 500 ml place, we put the nitrogen gas and we heat up to a certain 100 degrees centigrade so that it can generate the water vapor or moisture, and that will process to the that FR3 oil. It depends on the actual time scenario, like how long we can wait, or maybe up to till it get evaporation.
Okay, if you increase the time, for how much time you are passing the water vapor, does it affect the amount of moisture it is absorbing?
Yes, that is a good question. It actually depends on the time. Like if you put it for half an hour, you can expect up to, let's say, 100 ppm. So if you keep it for 2 hours, maybe you can get an actual moisture of 300 ppm. So according to our requirement, suppose I need to measure the breakdown voltage or like partial discharge inception voltage at 100 ppm, actual moisture. So I need to stop it there. Suppose we need to check every time, every 10 minutes, we need to check the ppm. What is the ppm now? So it may not be the exact. Suppose sometimes it's a practical scenario, it is very tedious. Like when you take the moisture, let's say you just now check it is 79. Maybe after 5 minutes it is crosses 100. So we need to be very careful. Every time someone will be there, every 5 minutes, take the syringe of water and check what is the moisture. So based on that, we need to stop that. We just take out that pipe and we check it, and we repeat that. Suppose this is the moisture, and we measure for 3 times. So if it is a range in that range, let's say, suppose 100 ppm, 102 or 103 or some range, then we go, okay, let's take its mean value. Then we can further repeat the process. Yes,
Hello?
yes, you are telling something. Yeah, you are telling something.
At a particular temperature, you have like maintained particular time, fixed time.
Yeah. See, there will be three variables here. Initially, I told two.
Yeah.
Here will be three variables. First is like, what is the oil temperature you want to measure? Suppose it is a room temperature. Then the first variable is omitted. First, let's say you are measuring in a room temperature, and you need to increase the moisture. Here, only you need to put the heat on the water container. Only 100 degree you put it, and that water vapor comes out and it's mixed with the oil, and you take the oil sample and check the moisture. In the second case, suppose I want to go for 40 degree temperature and moisture I want to keep it for 100 degrees, 100 ppm, sorry. So in that case, we need to put the container temperature here. Container temperature, let's say here it will be, let's say 100 degree, and we find out that there will be reflecting it is 100. Suppose you put it 150 degree, then you can get the temperature in the oil like 100 degree. So you need to measure the 100 degree temperature now. Then you put the oil, then they put the moisture in the oil. So then both the criteria will meet. 100 degree and moisture is let's say 100 ppm. 100 degree, then you go for the 200 ppm. 100 degree, then you go for the 300 ppm. So these are this is the way we did it.
Okay, thank you, sir. Thank you for your wonderful presentation. I have one other question, sir. You have shown the PDIV measurement circuit and PDIV result.
Yes, yes.
So what is the frequency band you have used for measuring this?
Frequency band, exactly. I forgot it is like Tektronix. I'll send you the details. Yeah, but we measure it in 60 hertz frequency. That frequency range, I need to just send you. I can send you that one. That exactly I forgot right now. But that is a very high-end Tektronix system. I exactly didn't remember it, but I'll send you the details frequency range of that one.
Okay, thank you, sir.
Welcome.
Any other questions? Okay, sir. May I ask you a few questions?
Please, please.
Okay. So, yeah, it's not actually a few questions. It can be quite a lot. Please bear with me. So, in the case of a normal power transformer or a high voltage transformer, the design stress in mineral oil would be somewhere around 1 kV per mm. Am I right?
Yes.
So what would the design stress be in the case of ester oil? Because in the case of mineral oil, we have a significant permittivity difference between the craft paper and the oil.
Yeah,
right.
Yeah.
For example, mineral oil has 2.2 permittivity, whereas ester oil has around 3.2, 3.3. So
yes.
The ester oil ideally would be stressed a little more than how much a mineral oil would be. So would the design stress change depending upon the depending upon what oil you use?
You are talking about with the load, design stresses in the oil changes, or like
No, I'm asking you whether there is a difference in design stress between ester oil and mineral
oil. Agree. There is a difference in design stress of ester oil and mineral oil. That we have to agree. That we all agree.
Okay.
Because
so will it be higher or lower, sir?
Design stress will also be higher.
Okay. In the case of ester oil, it will be a little higher.
Little higher.
Okay, and because of its viscosity, won't the heat transfer properties be affected?
Yes, good question. That is I was expecting. Because heat transfer is always depends on the viscosity of the oil. Since the ester oil is having high viscous, there will be a high heat transfer. Like thermal conductivity properties, the oil will be higher compared to your mineral oil. Mineral oil is low viscosity and easily flowable. Because because of the ester oil and palm fatty acid. Palm fatty acid is somehow the viscosity is somehow related near to mineral oil, not very high viscous because it is monoester. But in triester such as palm fat, your FR3, Jatropha, and other oils, those are triester. There will be having high thermal conductivity and high heat transfer. But there is a problem comes with the high heat transfer and high thermal conductivity, that is your circulation. And waxing also comes with the oxidation. These are the three problems. It's added with these advantages. But thermal conductivity will be higher.
Okay, sir. And one more question. So we all know that by thumb rule, for every 10 degree raise in transformer oil temperature, the breakdown strength drops by almost 50%. You would agree this as a thumb rule for mineral oil. So does the same relation hold good for ester oil as well?
That means you are telling that if temperature increases, the breakdown voltage decreases.
Yes, yes. So, but does it as drastically reduce as mineral oil does?
I don't agree with the statement because if the temperature increases, it's clearly because up to certain temperature, as I told, like up to 50 degree maybe, which is the operating temperature of the transformer. Less than 50 degree may be the operating temperature of the transformer. But in the experimental stage, if you experiment in the laboratory or something, it will go beyond the temperature, beyond 50 degree or 40 degree or 60 degrees, something. I don't think like this breakdown voltage decreases. It will be very different case to case. Maybe it will increases because of the chemical structure of the oil. Sometimes it is paraffinic structure. Maybe this with the temperature, this paraffin structure will break. Naphthenic structure, maybe it will break because of the high temperature, and maybe breakdown voltage maybe easily happen, or maybe there will be a change in breakdown voltage. But in case of ester oil, there because it was very densely packed, and when they will get a temperature, they will be free, and they will carry the charge and a very uniformly, or maybe in a very well manner way, so that the breakdown voltage will increase. That's what we experience with the high temperature, the breakdown voltage increases. That's why I took the responsibility of viscosity. Viscosity took the responsibility. Maybe there is a change of viscosity, so the breakdown voltage increases. But that may not be the exact answer to that. We need to evaluate more and more of answer to that.
Okay, sir. So one final question. So all these problems only occur when we use paper or kraft as the interturn or winding insulation. Yes. But currently there's, a lot of people are employing polypropylene as the interturn insulation, you might know, sir. So polypropylene has little to no water ingress almost. So would ester oil, and they also have the same permittivity as that of kraft for, for this thing, polypropylene, it's almost 2.3, and for kraft, it's about 4 or so.
Right? See, that I agree. Like, whatever the problems coming across our way, because of this, the combination of oil and the paper, both are like, one is hungry for moisture, one will be like always carries the moisture. So there will be a combination of like a very good combination between this. But if you want to use the polypropylene in case of kraft paper and press board, that will be equation, entire dynamics will be changed. It is not like there will be a lot of parameter will not consider at all. Like they will not consider about the moisture in the oil much, because the polypropylene will be not that much observant to the, like it has not affinity to attract the moistures. The entire dynamics or the entire mechanism will be changing. People are approaching for the dry type transformer. Somebody Many people have already worked in Japan for the dry type transformer. So I don't have much idea, or I have not carried out much experiment in polypropylene as a condition. So I think I'm not able to answer your exact answer to your question in that perspective. But I can say that like moisture along with like oil and paper, if you are studying, then there will be a problem always. We need to find out how we can do, because it is cheaper and easy to operate. That's why people are not leaving the oil field transformer.
And would the same application be applicable to OLTC also?
OLTC means OLTC means
On-load tap changes, because they have frequent arcing, no sir?
yeah. There's also that means wherever there is a like insulation bonding, or wherever there is a composite insulation, there also you can use this kind of thing. There will be a thing which will be happening like this. So whether it is my transformer or on-load tap changer, both the cases it will be. From my opinion, it will have to be same. But I don't know much about tap changer and what is their mechanism and all.
Okay, sir. Any other questions from the audience?
Yeah, I have a question.
Please.
Yeah, sir, for the partial discharge measurement, you have shown the PDAV and PDEV also. We like
Yes.
the change in PDAV and PDEV is not so much difference existing. So, which means that once we try to decrease, you went up to a certain level to check the PDAV, and then you come with the same decrement to 0 voltages, and you see that there is the voltage is getting reduced. So which means during the decrement you see a drastic reduction to less. You don't get PD at less than, for example, if you consider the first row, you see that 11.5 you see experience partial discharge, and then when you try to come down, you don't see any PDs less than 11 kV. Is it so?
Yes, correct.
Okay. Also, sir, you have shown the magnitude of partial discharges. Have you measured the phase resolved partial discharges? Like
you're talking about the PRPT pattern or PR that we have measured. That I have not shown here because we have not published that one. That's what I told you. Here we have measured like linear increment, and also we have measured like stepwise, like 1 kilovolt per second and hold for 2 seconds. Again 1 kilovolt up to same 15 kilovolt. We have measured in both the cases, linear increment, and we have studied the PRPD. So maybe so end of this year, maybe we can get some publication after that I may show you or something. May I know your name, please?
So my name is Amalanathan.
Amalanathan, okay.
Sir, can you please introduce yourself also, Amalanathan?
Yeah, I have completed my doctorate at IITM. Now I am pursuing my postdoc at Germany.
Oh, great.
I'm working.
Are you working with Stuttgart?
Not Stuttgart. I'm in Zittau, Hochschule Zittau, Germany.
Okay.
Sir, for the calibration part in the partial discharge, how do you, for reducing the noises, for example, in a conventional PD setup, we try to have a calibrator of known PD magnitude, and we try to calibrate the test cell. So what was the PD magnitude that you used to, for example, we have the calibrator from 5, 10, 20, 100 picocoulomb of known charge.
You are talking about the calibration range. Like we have studied up to 200 picocoulomb, from 10 picocoulomb to 200 picocoulomb, and we took that data for the further PRPD and the PD analysis result. So that calibrator also we have used before taking that. We change the charge magnitude, 10 picocoulomb, then what is the deflection, 20, 30, 50, and 100, 200, and we got that equation. And from that, we did this calibration and all. similar way that the way we're performing, a similar way, and also, yeah.
Sir, the next one is for the ester fluid. We do say that it can hold a higher moisture content, where it can increase the lifetime of paper. Whether the moisture content, holding capacity of moisture content in an fluid, insulating fluid, should be higher or lower?
It is a controversial statement. See, if there will be a moisture in the oil, that will goes to the paper.
Yeah.
Okay. And if there is a moisture in the paper, it
Yeah.
is already dangerous. So we definitely try to reduce as much as water content in the total devices, like in the either way. If during the installation we need to protect.
Sir,
During the
but there
pouring of,
is a conclusion saying that since ester fluid is more water hold, it has a more water holding capacity. People have shown that it increases the lifetime of paper insulation or the solid insulation inside the
yeah,
transformers.
they're telling that there is a, like, if there is a moisture in the oil, so much water will not be accepted by the paper, and it will be like a balance of the. I have studied this paper.
Yeah.
But I am not completely agree with the statement, like if the moisture in the oil will be higher or holding capacity will be higher, it will increase the lifespan. That is not at all, from my perspective, from my research perspective, I didn't think this is the correct statement. And again, from the beginning, I told it's a controversial statement, as long as we didn't come to a conclusion that it has some certain physics behind it. But still, if you avoid the moisture, it will be better for both the insulation systems.
So for the compared to mineral oil, we know that ester fluid has some different physical and chemical properties. For example, like the viscous property is much higher for the ester fluid compared to mineral oil. Should the design structure of the transformer should to be changed according to the ester fluid's physiochemical properties? So all or the existing mineral design specifications used for the mineral oil, we can just replace the mineral oil inside the existing design used for available in the market, or we should design the pressboard stacks which we design for the distance between the each stacks, where we need a good circulation for the wind to reduce the winding temperature, or conditions like that should be modified when we try to implement ester fluids inside the transformers.
Okay. See, there will be two perspectives to this like problems here. First of all, like if you want to change the whole transformer, like suppose you want to deploy the ester oil, you want to change the transformer design. I think to coming into the transmissibility, like suppose there is a mineral oil standard of transformer, you want to change the ester oil standard transformer, there will be much effort or labor should be put forward by the industry to make such kind of ester oil based transformer. Rather than that, what we suggest or what we think of, we can do it like, why don't we change the oil parameter such that it can accommodate in the transformer oil, or some added attachment to the new old transformer so that it can generate, such as, for example, circulation. Viscous oil such as like FR3, after using like if you have carried out the accelerated thermal aging or something, there will be a wax like structure, is always sediment inside the container that we have always. So how you believe that this oil in the transformer will not sediment or sludge, or that may be oxidized after some time? There is a possibility, high possibility or high chances. So there may be additional circulation techniques, or maybe there is a certain chemical changes or modification in the oil which is possible, so that it can be accommodated in the mineral oil based transformer. I don't think like changing the transformer will be a good idea at this present stage of time.
But then sir, now we are moving, since the depletion of mineral oil, I think some industries are also deploying such design modified ester fluids into the. I'm not sure with as far as our Indian country is concerned. I think now it's possible they have come up to some level of distribution levels of building up ester based transformers, whereas European countries, I think it has become common with the middle based synthetic and natural esters.
So like all Europe, Japan, and even in China also, they don't want to change mineral oil. They are happy with the mineral oil, and they also don't want to use this ester oil based transformer because they are good with their packing and they don't have any problem with or then issue with the transformer. Their transformer don't burst like Indian environment condition, because the transformer is quite sustainable here. So they are looking this research into very not very high or very priority way, but maybe time will come. They will also look into this way to change the transformer into ester oil or something. As per I visited some of the industry like Yucca Industries and Fuji Electrics. They are not in a favor of changing this oil, though they are carrying out the research of ester oil, but still they are not going to change the oil from mineral oil to ester oil, any kind of ester oil.
Sure. Maybe the climate conditions here
Climate
support.
condition in India is
Correct.
that is true.
Thank you so much, sir.
Thank you so much for
your beautiful presentation.
Thank you so much.
Thank you.
Any further questions can be emailed to Dr. Maharana directly, and we can facilitate all that. For now, I kindly request Dr. Maharana to very briefly share his personal approach and experience regarding.
Can I just exit from the screen? Like does it includes like on any questions, or I can stop the screen sharing?
Oh yeah, you can.
Okay.
Further questions will be emailed to you, sir.
Okay, no problem. It's okay.
And can you very briefly share your personal experience and career prospects of PhD scholars? Because you would have also undergone the same, routine.
India 130 kV transformer ester oil is commended data acceptability for the new challenges with the industry in India. Yeah, there is possibility, as I told. Okay, so my PhD journey was like what do you call the sprint. I joined after my master degree. After carrying out because I don't belong to electrical engineering. First of all, I completed my master degree from IIT Guwahati, mechanical engineering. That from computer assisted manufacturing. Post that, I was joined Center for Energy to carrying out PhD with Professor Sisir Kumar Naik, who is the now professor and carrying out the high voltage lab and experiment. So first 1 year, to be very honest, I was not in a very good mood, because I was in mechanical engineering coming to electrical and carrying out core high voltage engineering. It is really tough for me. But initially we studied about different nanoparticles and the application. I basically a material guy. I most work in and during my PhD was chemist or any chemical equipments like FTR, DAC, TGA, APM, ACM, nano indentation. I had worked during that. But Professor Naik has a lot of supported me a lot. He has given me the motivation, like, you carry out in this particular way. So we started working like how we can collaborate, like my expertise and your expertise, how it can be combined. So we started lighting a project to SCRB, Science Engineering Research Board, DST India. So it is based on the natural alternative liquid dielectric for power and distribution transformer. That's what in 2015. There we wrote a proposal and I put a lot of effort. I break my head to understand the electrical terminology. And finally we submitted project proposal, and fortunately by putting such great effort, it was accepted. And then we started working on it. And at that time, IIT Guwahati doesn't have any high voltage lab or any kind of electrical insulation monitoring equipment were not there. So we used to, since we have to do the all electrical analysis, chemical synthesis and nanofluid, we can prepare from the chemistry lab by taking the help of chemistry lab. But electrical insulation arrangement was really tough. That time, Munmun, she is also here. She has joined that time as a master student in our department. And we both figured out like where to go for the electrical insulation measurement. So finally, we found out the CPRI, where we had a discussion with currently he is the scientific officer, Manas Chakrabarti. And he guided us. He has all the testing equipment. We were blown away with the setup present over there. They have 10 delta, they have AC breakdown voltage, they have all the equipments they have that time we need. So we started without waiting for the project approval or project funds. We rushing into the experiment. We carrying out the experiment. We got this fantastic result about it. And we took the help of mechanical, we took the help of chemical, we took the help of CPRI. And our department had nothing that the project I was carrying out. So all are outsourcing. I was doing all the outsourcing part. And fortunately, many people from CPRI Bangalore and PGCIL Nuagaon, PGCIL Power Grid Corporation of India Limited, they are also came forward to support us, because that time I was the second PhD student and first to carrying out the high voltage insulation monitoring in the oil. That time that was not there in IIT Guwahati. So then, because I had previous experience in heat transfer arrangement and heat transfer measurement, so I took different support from different professors. I used to go to the professor and listen to them, and I throw my problem to them, and that professor may be of not from the same department, but he used to give some suggestions. So I take it forward, which is necessary. Then I by taking different outsourcing like PGCIL, CPRI, different department, and also NIT Alcala, whichever way the possibility is there to get this experimental result to be done. So we in the first 1.5 years, I completed almost all the experiment for the insulation monitoring of the oil. Then we moved to test this aging study, how it can perform the aging study and all. We moved to IIC Bangalore, and Jay Thomas, sir, Professor Jay Thomas, he also recommended us to go to CPRI. There also, their steps are very cooperative and they supported us. They saw us how the aging is being carried out and all. Post that, Munmun and me had developed an oxidative aging and setup that is also a patent now. After that, we had developed an accelerated thermal aging setup design that is a patent now. So by end of 17, almost the fluid part and all this experimental result in nanofluid has been done, and I published 1 or 2 papers at the time. The journey was not that smooth that I am explaining. It was every day is a hardship. And after that, I moved to Japan once for presenting the research work in IACIM 2017. I was also one of the person who was selected as the summer school. And in 2017, I won the best young presenter award in IACIM. The time before that time, 2015, I think Niharika Barua also joined with us, and we had a great bonding together. Those guys from Assam, so I am from Odisha, so they talk with the Assamese people in PGCIL and Nuagaon. We try every possible opportunity which is available outside to get the experimental facility, and a simultaneously project has arrived in 2016 March. And the project commissioned, and we tried to buy some equipment, and we got the frequency analyzer. By 2017, end of 2017, I almost completed all the experiment, and we published 1 or 2 papers. I think at the time it was accepted. That time, a lot of pressure from my family to get married. So in the meantime, I wrote a letter to Professor Naik that please release me. Just I have completed 3 years. Three professor, two from mechanical and com, and console me like, okay, you just in the very good stage of your life now, you are carrying research in a very good way. The console was really good. They really motivated me. And 2018 August, I submitted. Like, well, I think from the department, I'm the first guy who submitted the PhD thesis in 3.5 years, almost 3.5 years. I joined in 15 January. I submitted in 2018 because I was there. New to this topic, and the time nanofluid research was not very vast in the insulation field. Very less people, like in the University of Delft or some Manchester University, some people have carried out. Then it was submitted. I went for a job. Then in 2018 October, I went to CIDP Mexico. That also I met some of the professors. There I got to meet Professor Ukai, who is the current boss of mine now. So he gave me the opportunity, you can come and join my high voltage lab. So after that, we wrote a paper both together, and I joined post that 18. I submitted, and I went to private engineering college to carry out job. And in April 2019, I defended, and after that, I built a strong collaboration with different professors during the conferences. I used to go to the people because when I saw their work, because maybe the people from Europe or some different part of America, they'll not discuss with you at front unless your work is very much scientific and physics driven. So if you want to discuss, or if you want to get an opportunity, go and discuss what could be the possible probability, or what is the possible option to for a solution or for a mechanism. So they will give a suggestion. In that way, I try to interact with the people. Like I always wanted to get some new idea. So that idea took me like different discussion. I usually discuss with the people. And post that in 2019, out of this research, high voltage research, and my own interest was different. Like I was working on the elbow decirculation prosthesis, which is entirely different. It's my master thesis work. So that time I applied a young Gandhian Young Technological Innovation Award. I developed one artificial elbow joint, which is earlier it was very aesthetic, was not good, and material was not that very good. So they selected me in 2019 July. I got a vice president award for that. And after that, I joined here in State Laboratory Installation and Power Equipment, and till now it is going on, and I doing the collaboration with different university from my possible aid, whatever the skills or experience I have, I usually share. And the people, if they accept, they collaborate with me. And if sometimes somebody asks for me to help, I usually support. I collaborate with them. It's a mutual collaboration. I feel scientific collaboration and is very much necessary. I felt like the questions were asked today was really good, and the kind of question I faced today from Germany, India, and peoples. I think the research is really going on, and if at all, if you need any kind of research discussion or support or collaboration, I'm always open for it. You can go ahead with this. Yeah, that's all. That's all about my PhD and research journey.
Okay, sir, that was very insightful. Thank you. It is indeed a pleasure to have such a person of your caliber on board, Dr. Maharana, and it is in that regard, please accept the virtual token of appreciation on our behalf of the IEEE DA Student Branch Chapter IIT Kanpur.
Thank you so much. Yes.
And if the
Please,
audience are available, can we all have a quick, sir?
Please share me this photos or this
PDF. Yes,
version.
definitely.
It's really an honor.
Can I have all the audience on board to share their videos? I mean, can they start their videos so that we can have a quick group picture?
Oh, hi, Niharika.
And hello, actually, I'm a bit outside.
The soft drinks are complimentary.
Nice presentation.
Thank you. It's okay. It's okay.
For one.
I request all participants to turn on their cameras. Darshan, please take a photo of all of us.
Done. Okay.
Yes, done, sir, done.
Thank you so much, guys. I'm really honored and happy to be here with all of you. Such a nice audience, and I really enjoyed discussing with you guys.
Sir, it was a very engaging talk. Thank you. So, the successful execution of the webinar would have not been possible without the efforts of the entire IEEE DIS SPD team at IIT Kanpur. I also would like to express my sincere gratitude to the IEEE IIT Kanpur student branch chapter and the IEEE UP section for their invaluable support. In addition, I also acknowledge Dr. Alok Ranjan Verma, our faculty advisor, and Dr. Nandini Gupta, our mentor, for providing their valuable guidance and support. And to end and commence, we will thank all the audience for their presence and making this event a great pleasure. Thank you very much.
Thank you, everyone.
Thank you, sir. We can leave, sir.
Yeah.
Thank you.
Please.